Hello everyone and welcome back to another pre-calculus lesson. I'm very excited about today's lesson because we're continuing our adventure through trigonometry, which is one of the more useful and, in my opinion, one of the more beautiful parts of the pre-calculus curriculum. When I say useful, this of course means it's useful in terms of applications toward calculus and physics and things like that. So last handful of lessons, what we spent time trying to learn how to do is we understood how to measure angles, we learned radians, and we introduced reference triangles, and we learned, for example, why trigonometry starts with the prefix tri, because it's all based off triangles. And we introduced sine and cosine, and we talked about the sine, cosine, tangent, and how these functions are going to be defined, and we introduced some of their properties. However, a question that we have not really tried to answer in any robust way is, how do these functions literally look? That is, if we were to graph them on a Cartesian coordinate system, what do they look like? Well, in the spirit of this class, we've guided our curriculum by trying to answer two questions. We start by asking what kind of functions are out there, and then we want to know how they behave and interact with one another and how they look. So, in the pre-calculus portion of this class, we're going to try to address the latter question. To begin with, we start like we did every time we introduced a new function. We take a look at a table of values, and then from that table of values, we're going to try to sew them together to build a cohesive picture. So here we have a nice incomplete table. We have a handful of inputs, whereas in previous lectures, before trigonometry, we might have had inputs like 0, and then maybe we would have done like a -1 or a +2. But since we're trying to graph sine and cosine, it's important to choose our inputs, these angles, in a reasonable way. So we're going to choose angles that we're familiar with, angles that we discussed in the previous videos. And then if we plug them in, we're going to witness that, for example, sine at 0 degrees is going to be 0. Sine at pi/6 radians is 1/2. Sine at pi/3 radians is √3/2, and we can continue in that fashion. As we move forward, we have to get more adept at being able to do this type of computation quickly. So we'll just run through the missing values here. Sine at pi/2 is going to be a 1. At 2 pi/3 is a √3/2. And I might take a pause here and say that it might be fruitful for you at home to go ahead and try to fill in this table, pause the video, try to fill in the rest of the table on your own, and then resume the video and compare and contrast. Continuing, however, the missing values are at 7 pi/6, sine is -1/2, at 3 pi/2, sine is -1, and at 5 pi/3, it's -√3/2. You notice that there are some trends here. We seem to be going from 0 to 1/2 all the way up to √3/2 to a 1, and then we seem to march back down exactly the way we came. So we're kind of going up a mountain and then down a mountain. And then we're going negatively down a valley and then up the valley. For cosine, the missing values at pi/3 is a 1/2. At 5 pi/6, we get -√3/2. At 4 pi/3, we get a -1/2. And at 11 pi/6, we get a √3/2. Now what we notice is that there's a little bit of an identification between sine and cosine. For example, you might witness that here is a 0 and a 0. Then we get a -1/2 and a -1/2, a -√3/2, -√3/2, a -1 and a -1, -√3/2, etc. And what we see is that there's this identification that somehow the values of cosine seem to just be shifted values of sine. If we took these values of sine and just moved them a few bits to the left, we would literally get the values of cosine. So this is hinting at some sort of underlying relationship between sine and cosine, and we'll revisit that in just a moment. So what we're going to do now is we're going to plot some of these values on a Cartesian coordinate plane, and we're going to play connect the dots. So for the first graph we have up here, we're going to graph our sine function. And just like every other graph we've built in this class, there's a couple of what I might call key points that we want to make sure we draw. Those are going to be the quadrantal points. Those are the points corresponding to the quadrant angles 0, pi over 2, pi, 3 pi over 2, and 2 pi. So for sine, that's going to be a 0, 0. So that's this point. At pi over 2, sine is a 1. At pi, sine is a 0. And at 3 pi over 2, sine is a negative 1. And at 2 pi, sine is a 0. It's important to remember that trig functions are smooth functions. They're not exactly a bunch of lines. We're going to have a very nice smooth transition between the dots that we've built. For example, at pi over 6, which is maybe right here, we seem to have a point at 1/2. Well, there's 1/2. We seem to have a point right there. Notice that it's not a straight line between these two quadrantal angles. It does seem to curve up first and then hits this peak at 1. So keeping that in mind, you can plot as many of these test points as you feel necessary until you can conclude that your graph should look something like this. There we go. Now, of course, due to coterminality, we could have plugged in more points over here past 2 pi, and that would have drafted points on this Cartesian coordinate plane to the right of 2 pi. But due to coterminality, we would have ended up building just another copy of this curve. Similarly, to the left of 0, we could build another copy to the left. And since the domain of a sine function is all real numbers, what we've drawn here is just one chunk of the overall curve. It actually continues on forever in both directions. So if this is sine, we can do the exact same thing for cosine. And so if you plot some of those points, the quadrantal angles are 1 at 0, 0 at pi over 2, negative 1 at pi, 0 at 3 pi over 2, and 1 at 2 pi. Where again, we can play connect the dots in sort of a smooth fashion, and our goal here is to draw cosine. In the smooth fashion, it might look something like this. There we go. Now, it's important to note that this relationship we saw that I highlighted in green claimed that the values of sine are kind of just a shifted version of cosine. And what we see in this graph is that this is a true statement. In fact, cosine is just sine shifted pi over 2 units to the left. If I take the sine function and I literally pick it up and I move it pi over 2 units to the left, that is, this pi moves here, this 3 pi over 2 moves here, the 2 pi moves here, we're literally just going to build the cosine. So sine and cosine are actually just horizontal shifts of one another. Nonetheless, we still treat them as independent parent functions because it kind of just makes our lives a little bit easier. Now, let's recall some of the facts we know about sine and cosine. We learned in the last few videos that the domain for sine and cosine are all real numbers, negative infinity to infinity. We noted that the range was negative 1 to 1. We can now confirm that with our pictures up here. Due to the fact that coterminality exists, we remind ourselves that these functions are periodic and the period is 2 pi. What that again means is that these pictures up here are just one representative chunk of the sine and the cosine graph respectively. They're representative chunks because everything to the right and to the left of these chunks will just begin replicating the exact same curve. These are the unique parts of the curve between 0 and 2 pi respectively. So we do have that these graphs are periodic with a period of 2 pi. And then we might recall that sine is odd and cosine is even. What that means is that if I were to graph these two functions, I should get some symmetry out of the graph as well. Now with that being said, what we can now do is we can graph sine and cosine, but we don't necessarily have to restrict ourselves from just 0 to 2 pi. We could force ourselves to graph on the domain negative 2 pi to 4 pi. Well, that's okay. The graphs we saw on the previous page might look like the following chunks. I'm going to graph sine in blue. And so what we saw is that from 0 to 2 pi, we had that sine was 0 at 0 and 2 pi. It was 0 again halfway in between. And then, so this is at pi. And then halfway between 0 and pi, we got all the way up to the peak of 1. And between 0 and 2 pi, we got all the way down to the valley of -1. These, again, are the key points for sine, and that's why I graph them first, so that then we can connect the dots in a smooth fashion. There we go. So what I've just drawn right here is a sort of zoomed out, squished version of exactly what I drew right here. The difference, of course, here is in this picture, I'm restricting my view from 0 to 2 pi, and in this view, I'm zoomed out a little bit. But because we're zoomed out and because we've been asked to draw in a slightly different way, here, since the period of sine is 2 pi, and between -2 pi and 4 pi, there are 3 copies of 2 pi living in it, we're actually going to have to draw this curve 2 more times, once to the right and once to the left, so that we can graph from -2 pi to 4 pi. But that's okay. It simply amounts to drafting your quadrantal angles again. So we know that 2 pi later, we're going to hit 0 again, and then we're going to hit the valley a quarter of the way, and then a peak a quarter of the way, and a valley 3/4 of the way through the period. So then we can connect the dots. Similarly to the left, 1 period away, all the way out to -2 pi, I'm going to hit 0 again. I'm 0 halfway between, and then we hit our peak during the first quarter and our valley during the third quarter, so then we can connect the dots. And there we go. This is our sine function living between -2 pi and 4 pi. The cosine function runs very similarly. I'm going to graph that in green. The only real difference is that these main quadrantal key points that I drew, I'm just going to draw the cosine ones instead, meaning I'm going to start at 1. I'm going to 1 period later at 2 pi, end at the same point. Halfway between that, I'm going to come down to -1. Quarter of the way I'm a 0, and 3/4 of the way I'm a 0. So I can again connect the dots in a nice curved way. And then I can do the exact same thing to the left and to the right, so that I can build all 3 periods of the cosine function that live between -2 pi and 4 pi. So to the right, I'll end up to 1 period later hitting a 1, halfway between hitting a -1, 0, 0, connect the dots. And to the left, we're going to hit a 1, -1, 0, 0. And we can again connect the dots. And now with 3 copies of the period, we can see very clearly that indeed the cosine is just the sine shifted pi over 2 to the left. By the way, if this looks at all like a double helix to you, that's probably true, because in fact, a double helix DNA strand is modeled by sines and cosines. So there's a lot of really good future applications of these concepts. Now that we know how to graph sine and cosine, we can now talk about our favorite parent function transformations. More or less, they're going to function exactly the same way, and what you want to look out for is you want to look out for what happens to the x-intercepts and the local max and mins. Those are what I'm calling my key points. Once you figure out where those go, you then simply connect the dots between them. Now, the development of trigonometry historically was not done by mathematicians. It was done by physicists. So they came up with all of their own sort of naming system for how everything works for sine and cosines. So it's going to be a little bit different from what we're used to. For example, if I consider my sine function, but with an a sitting out front, we would ordinarily have called this a vertical stretch or compression. In this case, we're going to call it an amplitude. Additionally, if there's a negative sitting out front, this is of course going to induce some sort of a x-axis reflection. So if I wanted to graph -3 sine of x, there's a couple ways I could try to do this. One way I could do this is I could start by graphing my sine function. I could go up to 1, and then I could go down to -1, and then I'm going to start sine at 0 at 0, 0 at 2 pi, and then we're going to hit 0 halfway in between. I'm just graphing those same key points. And then I could connect the dots. And what I've drawn here is sine of x. That's drawn in blue here. Then what I need to do is I need to reflect it. So I'm going to introduce this reflection right here. Now I'm going to draw a negative sine of x, and that's going to be drawn in green. And all that's going to do is it's going to keep the zeros. It's just going to flip what was positive to negative and negative to positive. So that's going to look something like this. And now I need to vertically stretch by 3. And this is where things get different depending on what book you use. I'm going to teach you what I think is the easiest way to graph these functions without having to rewrite and redraw your graph a million times. The way to do that is, notice that when everything stretches, effectively what happens is this 1 is going to have to get blown up to a 3, or this -1, I should say, is going to get blown up to a -3. I could sit here and say, okay, fine, let's grab a new color and then make it go, all the way up here to a -3 and all the way up here to a +3 and then come down. I could do this. So I could say that, in this case, -3 sine of x is now drawn in orange, where, it's coming down to -3 and it's going up to +3. Or, since we are in charge of our drawing, we are in charge of our scale, I can instead choose to do something slightly different. So if you want to redraw our steps so far and then add in the following, that's fine. I'm going to opt to erase. I'm going to say, instead of drawing this stretched version, why don't we just go back in time, erase all of that content, erase that curve right there, and instead, I'm going to simply take my green and I'm going to erase those scale markers, and I'm just going to change it to a 3 and a -3. And now what I've drawn is not negative sine, but what I've drawn is -3 sine. And there you go. Now, of course, it looks slightly different, but we are in charge of our scale and our axes. And so once we give ourselves the freedom to label our tick marks where we want, it actually makes our lives a lot easier. Now, this freedom is going to be a little intimidating at first, but once you get a little more comfortable with it, it's going to be a lot easier to work with. So let's keep that in mind as we move forward. Here we have -1/2 cosine. So the way I'm going to do this is, again, I'm going to start with blue. I'm going to draw the parent function, cosine. And let's see. I'm going to draw this very tiny like. So the cosine function starts at a 1 and will end at a 1. Halfway between, it goes to a -1. And then it hits 0 between those marks. And so the cosine that I'm drawing is going to look something like this. Now, I purposely drew this very thin and very light because this is not my final draft. What I need to do now is I need to amplify it by a -1/2 and reflect it. So to do that, I'll do that in green. So let's bulk up our pen size, -1/2 cosine of x is now going to be drawn in green. Here, what I'm going to do is I'm going to scrub away the 1 and write that as a 1/2. Scrub away the -1, make that a -1/2. I'm going to reflect it. So the positives become negatives and the negatives become positives. And my final graph is going to look something like that. So we're going to have to get more comfortable with this idea of augmenting our axes and our tick marks in order to use them to our benefit. Now, if we can do vertical stretch and compressions, we need to now address what happens horizontally. Now, the first thing we're going to encounter is what happens when we multiply the inside of the trig function by a value, in this case, say 2. Recall that in terms of parent function transformations, what this should do is this should induce a horizontal stretch or compression. But if I were to take a curve like this cosine and I were to horizontally compress it, effectively what it's going to do is it's going to start making it oscillate faster. And if I stretch it, it sort of elongates its oscillation. So what that means is that the amount of time it takes to go through one period is either going to get multiplied or divided. We're going to call this its period. So if I take a function f of x equals sine bx, where that b is any value I want, we now say that its period is going to be 2 pi over b. It's no longer going to be a periodic with period 2 pi, but now it's going to be periodic with period 2 pi over b. So the very first thing you do when you encounter a function that's written like that is you have to go to the side and compute its period. This period is going to be 2 pi over 2, which is going to be pi. So what that means is that this function is going to go through its entire cosine wave after elapsing only pi units on the x-axis. And so what you'll notice is now I've removed all the tick marks on the x-axis. That's because we're giving ourselves the freedom to draw this how we want. So how do we do this? What I'm going to do is I'm going to realize that from 0 to 2 pi, which is where we want to draw this, there are 2 iterations of pi in that time interval. So that means I'm going to actually have 2 cosine waves from 0 to 2 pi. So first I'm going to interpret 0 to 2 pi. I'm going to put those on my x-axis. Then I'm going to give myself enough tick marks, pi living in between, maybe pi over 2 living between that, and 3 pi over 2 living between that. And what I realize is that from 0 to pi, only on this half, I need to go through an entire cosine wave. So I'm going to draw that. So we're going to go up to some crest and up down to a valley, and we're going to draw our cosine wave, which again has zeros, starts at 1, goes down to a low of -1, back up to a high of 1. We're going to connect the dots. There's our first period of cosine, and we're going to do the exact same thing over here on the right side. We're going to pick up our second period of cosine, like that. And then because the amplitude has a 7 sitting up front, we're going to go up to a 7 and down to a -7. And there we have it. This is 7 cosine 2x, which the 2x inside has squished our function by a factor of 2 horizontally, meaning that it has divided the period by 2, which is why we have 2 periods of cosine occurring in what used to be only 1 period's worth of 0 to 2 pi. So if we multiply by 2 on the inside, it forces our period to get smaller, and so we see more of these sine or cosine waves. If instead we divide by 2 on the inside, that's going to have an opposite effect. So let's take a look at what happens here. We're going to draw this one in green. So here the period that we're looking at is still going to be 2 pi over the b value, which in this case is a 1/2. Keep, change, flip turns that into a 4 pi. This is important because now what this means is that I'm going to get an entire sine wave once we get to 4 pi. So if I were to draw this curve from 0 to 4 pi, I'm going to get one sine wave. But notice that we only want to draw the function from 0 to 2 pi. So everything from 2 pi to the right is actually not what we're looking for. Now I'm going to draw it anyway because it's going to make my life easier, and then I'll just erase it when I'm done. So what we're going to have is we're going to have a negative sign, so that means everything is flipped. And so the sine function is going to start at 0. It's going to come down to its valley first instead of its peak because it's getting reflected over the x-axis. It's going to come back to 0, and it's going to go up to its peak, and it's going to come back to 4 pi. And so to the left of 2 pi, we're going to have that bump, and to the right of 2 pi, we're going to have that bump. And if I choose to go up to 3 and down to negative 3, this is one period of g of x. But this is an incorrect answer because I wanted, yes, we've graphed one period from 0 to 4 pi. However, I didn't want a period from 0 to 4 pi. I wanted only what it looks like from 0 to 2 pi. So what that means is that this component to the graph over here doesn't actually exist in our answer. The only answer that we want is what's going on right here. This is going to take some getting used to and some practice to understand this a little bit more. The key takeaway here is that when I multiplied the inside by a value larger than 1, it shrank the period, and so I got more copies. If I divide by a value on the inside, that stretched the period, and therefore I got far fewer copies. In fact, here I only got half a copy from 0 to 2 pi. So what we've done now is we talked about vertical stretch and compression and horizontal stretch and compression. What we want to now talk about is shifting. So maybe we'll take a pause in the video right here, and then we'll start the next video with horizontal shifts.